SwayamPrabha. Digital India. Educated India.
Hello everyone. We will continue our scales of turbulent motion analysis even further today. In the last class, what we did was we actually looked at the inertial subrange and the energy containing range. And the class before that, we looked at the dissipation range, the dissipation spectra. We looked at the dissipation spectra. We saw where the bulk of the dissipation was contained. We looked at the inertial subrange and realized that if we plot the compensated spectra, you could see that it actually turns out to be a constant value in the inertial subrange, which makes sense because the way the model spectra was constructed, it was like that. But the interesting observation was that experimental data also suggested that and showed evidence of that. In the energy containing range, what we did was we did something very similar to the dissipation spectra, where we looked at the cumulative kinetic energy. And we saw where most of our energy was concentrated in. So 80% of the energy was concentrated between 1/6 L11 and 6 L11, isn't it? So we will actually discuss that further today as well when we are discussing the transfer spectra. But right now, next what we are going to look at is what is the effect of Reynolds number on the model spectra. So here, no experimental data are shown, only the model spectra. The model spectra at 4 different Reynolds numbers, 30, 100, 300 and 1000. So these lines represent the model spectra that we had earlier shown. That spectra is determined, analytically calculated for 4 different Reynolds numbers and plotted. But there is a difference between the 2 figures shown here in this slide. On the first figure on the left, what you have is E of kappa, okay? E of kappa, which is divided by kappa KL11. So it is normalized using the turbulent kinetic energy and the integral length scale. On the right side figure, it is shown here E of kappa divided by eta u eta squared. So couple of things. One is on the left hand side figure, we did normalize it by a quantity that depends on the large scales. Turbulent kinetic energy, which is basically the total turbulent kinetic energy of the spectra, which is essentially where all the large scales are occurring, right? Because the large scales are contributing to the turbulent kinetic energy, so we are dividing it by K, and also L11, which is an integral length scale or a large length scale, the largest length scale if you will. And on the right side plot, we have the energy spectra normalized with eta u eta squared, which is a small scale phenomena. Eta is the Kolmogorov scale and u eta is the Kolmogorov velocity. So we normalized it in such a way that the right side, you should be familiar with it because we have normalized it in such a way before. And obviously, because we have done that, as a consequence, we see that the universal equilibrium range overlaps. And it is indeed universal. Whereas on the left side plot, it is not going to be universal because we have normalized it with KL11. And what we are noticing is, you might think that because we have normalized it with KL11, there is some kind of universal behavior here. That is not true. It looks similar. It is not identical. If it was universal, it would be identical. Here, it is similar. That is all we can say. I am talking about the large scales, right? This is the energy containing range. They look similar, but they are not the same. They are not identical. Okay. Now, few other observations we can make. For the energy containing ranges of the spectra, that is between 0.1 and 10, the spectra is very similar. Okay. which makes sense. So whereas with increasing r lambda, the extent of the negative 5/3 region increases and the dissipation range moves to higher values. That also makes sense. The fact that you are shifting more and more towards the right, I'm talking about this figure here, you're shifting more and more towards the right as the R lambda increases also makes sense. Why? As the Reynolds number increases, the gap between the larger scale and the smaller scale increases. We have scaled it in such a way that we are seeing very similar behavior for the large scale. So then what will happen to the small scale? It'll keep extending. It'll keep getting smaller and smaller. That is what you're seeing here. The wave number range, the dissipation range is getting extended. The inertial subrange is getting extended. Essentially, the universal equilibrium range is getting extended. It's becoming bigger and bigger. If you see for R lambda is equal to 30, you have a relatively smaller universal equilibrium range. It's only this much. Whereas here it is this much. Here it is this much. Here it is this much. Isn't it? As the Reynolds number increases. So that is the main observation from the left figure. Now for the same spectra normalized by the Kolmogorov scales, now here you're normalizing it with the Kolmogorov scales so that you can see the universal equilibrium range, and that would indeed be universal. And here also the dissipation ranges are very similar, while the energy containing range moves to lower values of k eta as R lambda increases. What do I mean by that? If you see here, as the Reynolds number is increasing, I am going up and up, meaning my energy is keeping on increasing with higher the Reynolds number. I saw that earlier when I looked at the total 3D spectra normalized, right? When I looked at with the experimental data as well. And I'm seeing something similar here. As the Reynolds number is increasing, I am going up and up on the y-axis, meaning my energy content is increasing with increase in Reynolds number. That makes sense. That makes sense. My energy content would increase as I increase the Reynolds number, and that is what I'm seeing here. So those are my two main observations from the two plots. Okay. So what we saw was the effective Reynolds number. Effective Reynolds number when we scaled it with the large scales, so KL11, and when we scaled it with the small scale, so eta U eta squared. And you can see the universal behavior was evident, and the non-universal behavior of the energy containing range was also evident. The next thing we are going to be looking at is the energy containing motions, and specifically we are going to be looking at the energy cascade, and we are going to be looking at the energy cascade in spectral space. So it's a spectral view of the energy cascade. Now, a couple of points before we start to discuss this more specifically. The bulk of the TKE is contained in motions of length scale, which is between 1/6 L11 and 6 L11, isn't it? We discussed that in the last class itself, and that is how we get our energy demarcation length scale of 1/6 L11. Now here the characteristic velocity is of the scale k to the half. It is of the scale k to the half, because U is square root of turbulent kinetic energy of the scale. We are not saying it is equal to. The other thing is this LEI or L11 is that size is comparable to the flow dimension, and the flow dimension is your fancy L, your characteristic length scale. So the large scale motions are significantly influenced by the geometry of the flow. All right. There is a time scale here as well. That integral time scale. That integral time scale scales with L11 over k to the half. Why? Because it is length over velocity, and velocity is k to the half. So it is L11 over k to the half. Now this is large compared to the mean time scale. So in that sense, the mean flow time scale, because the mean flow time scale includes all the time scales, right? So this is a large time scale. And in that sense, they are significantly affected by the flow's history, because this is a very large time scale. So the flow history does matter. If the time scale was very quick, very small, then things are happening very quickly. Then the history the flow's history does not affect the scales as much. Whereas if you have a large time scale, then the scales are indeed affected by the type of flow history. So in contrast to the universal equilibrium range, the energy containing motions do not have a universal form. We already knew that, brought about by some kind of statistical equilibrium. We already knew that. And all the anisotropy is confined to this energy containing range, right? Anisotropy means the directional biases. They are all confined to this energy containing range because the universal equilibrium range does not have any such directional biases. It is isotropic. And here, the other point is all of the production happens in this range, the energy containing range. Production of what? Production of turbulence happens in this range. And also, finally, viscous dissipation is negligible in this range as well. So what happens during this energy cascade process? So now that that framework is set up, as in what does the energy containing range involve? Now that that framework is set up, what actually happens in the energy cascade? So during the initial steps in the cascade, what happens is energy is removed from inviscid processes. Why am I saying inviscid processes? We have discussed this previously. Just think about the Navier-Stokes equations. The energy, the breakdown of the large scales happens because of the inertia term, the u du dx term, the inertia term or the velocity gradient term. So that is an inviscid process. That has no viscosity in it. So that is what leads to the scale breakdown, which means as in the initial step, energy is removed from the large scales through this process, and then they are transferred to the small scales at a rate, let's call it tau ei or TEI, let's call it TEI, which again scales at, this is the energy transfer rate. TEI is the energy transfer rate, which will scale as the energy, the rate at which energy is transferred, which will scale as u squared over time or u cube over L or k to the 3/2 over L. That is what I'm getting it like this, k to the 3/2 over L11. That is the rate at which the energy transfer rate scales. So this transfer process depends on non-universal energy containing motions, of course, because it starts from the large scales which are anisotropic, which are non-universal and which contain most of the energy. So in that sense, as a consequence, the non-dimensional ratio TEI divided by k to the 3/2 over L11, this is basically scaled, right? TEI divided by k to the 3/2 over L11, it is not universal. It is non-dimensional. That is the way we have scaled it, because TEI is the energy transfer rate. So u squared over t, u cube over L, or k to the 3/2 over L. So this divided by this, TEI divided by k to the 3/2 over L11 would be non-dimensional. Yes, but it is not universal. Nothing in the energy containing motions would be universal, isn't it? So that's that. Now let's look at the energy spectrum balance equation. You would think that if I have an energy spectrum balance equation, del T of E of kappa, it depends on three things. Energy is being produced, energy is being transferred, and energy is dissipated. Right? Produced in the energy containing range, over the inertial subrange it transfers, and in the dissipation range it dissipates. So on the RHS, I have production, I have spectral transfer, and I have dissipation. Now, this production spectrum, we won't go into the details of that, but it is given by the product of the mean velocity gradients. And we knew that it is an inviscid process. The production is an inviscid process. Energy is removed from the large scales, produced there, right? And an anisotropic, so it is the product of the mean velocity gradients and an anisotropic part of the spectrum tensor. Let that be. Let's not focus on that. Let's see what it means. The contribution to the production from the wave number range is denoted by, so you could, just like you have a dissipation spectrum, just like you have an energy spectrum, you have a production spectrum as well. And the production spectrum, the contribution to the production in the wave number range of kappa A to kappa B is given by integral kappa A to kappa B, the production spectrum integrated, right? P of kappa, d kappa. All right, so that's production. The second term has to do with the spectral energy transfer rate. And here what is happening is energy is transferred from the large scales to the small scales, isn't it? So it is essentially transferred from the low wave numbers to the high wave numbers. It's transferred from the modes of low wave numbers, lower wave numbers lower than kappa to wave numbers higher than kappa, because it goes from low to high. The rate of gain of energy in the wave number kappa A to kappa B due to the spectral transfer is, since this is a spectral transfer rate, what we'll be integrating is del k of T of kappa, T kappa of kappa d kappa from kappa A to kappa B. And since it is basically you are trying to find out what is the rate of gain of energy, that is why you're taking d of kappa, d kappa, or del kappa I should say, derivative with respect to kappa. Here it is only in the wave number range of kappa A to kappa B. And since you are taking an integral of a derivative, it comes out to be tau kappa of kappa A minus tau as T kappa of kappa A minus T kappa of kappa B. So essentially the difference between the two endpoints. I hope this is clear. Here what I have done is I have tried to find out the rate of gain of energy in the wave number range due to the transfer. So the rate of gain of energy with respect to wave number, and I am integrating that to find that out. Okay, so that would be T kappa of kappa A minus T kappa of kappa B. This term here is the second term in the energy spectrum balance. I am just integrating that term. I integrated the production spectrum. Now I am integrating the second term in the energy spectrum balance equation. Now keep in mind, there is no transfer from the lowest wave number of kappa is equal to 0. Why? Because there is no energy below that. Also, there is no energy, there is no transfer at the highest wave number of kappa tends to infinity, because there is no energy beyond that. There is no scales beyond that. In that sense, this value vanishes at 0 and infinity. So the transfer term makes no contribution to the balance of TKE. Understood? The transfer term makes no contribution to the balance of TKE, because if you think about it, if I just integrate this entire equation, on the left hand side if I integrate it, I should get turbulent kinetic energy. And if I integrate this from 0 to infinity, this term would go to 0 if I integrate it from 0 to infinity, because it is T kappa infinity minus T kappa 0, which is 0 and 0. So it comes out to be 0. That is what we mean by that. The final term is the dissipation spectrum. We have already looked at the dissipation spectrum. Now here, d of kappa t is 2 nu kappa squared E of kappa t. It is this dissipation spectrum which we earlier plotted and looked at how the behavior is. Fine. So that's that, right? This is how it looks like. So you have the entire wave number range. This is your energy demarcation length scale. This is your dissipation demarcation length scale. As you can see, the energy spectrum mostly peaks in the energy spectrum mostly peaks in the energy containing range. Then you have between this range, you have the E of kappa, and then D of kappa becomes prominent in the dissipation range. The production is dominant in the energy containing range, whereas the transfer starts to peak, keeps increasing, starts to peak in the inertial subrange and then decreases as well. So what we have seen is this energy spectrum function. Okay, so here this is the energy spectra and the dissipation spectra. Energy spectra is mostly dominant in the energy containing range, and dissipation spectra is mostly dominant in the dissipation range. That's what is showing. Here you have the production spectra, which is mostly dominant again in the energy containing range. This is the transfer rate, which starts to be more dominant in the transfer rate. It is del t of del t del kappa, right? Del T, del kappa, which is more dominant in the dissipation range. This is the total dissipation. This is the rate at which energy is transferred with respect to time, and this is minus del Tk del kappa. So here you are losing energy from here, and then you are gaining energy here. So it is not like that term is zero in the energy containing range. It is just negative. It is positive here. That is all it means. That negative del T del kappa is negative here and it is positive here. The transfer itself starts from 0, ends at 0, and it starts to peak in the inertial subrange and then decreases. Because as you get to higher and higher Reynolds numbers, your scales are reducing, and in that case your energy transfer, your rate of transfer actually starts to decrease. It is 0 to begin with, it keeps increasing, it peaks in the inertial subrange, and then it keeps decreasing. So that is essentially what we are saying. So in the energy containing range, all terms are significant except for dissipation. Okay, all terms are significant except for dissipation. So let's say, for example, the turbulent kinetic energy 0 to kappa EI is approximately equal to K, because turbulent kinetic energy is primarily in the energy containing range. Epsilon here would be 0 because there is no dissipation. Production is mostly contained in the energy containing range, and so hence it would be equal to the total production. The transfer itself at kappa EI would be equal to TEI. Why? Because in that range, T at 0 is 0, isn't it? T kappa at 0 is 0. T kappa at 0 is approximately 0, which means T kappa at kappa EI is TEI. This is, so when it is integrated over that entire energy containing range, that is 0 to kappa EI, the energy spectrum balance will yield dk dt. You have only production and you don't have dissipation, so you have minus TEI. Why? Because from here you would get T minus, isn't it? You would get minus TEI minus, and this is minus of TEI minus T0, which is 0. So that is how you get minus TEI. So dk dt is production minus TEI. So there's more analysis to be done in terms of each of these terms, and that is what we will do starting in the next class. But here what you have to understand here is, in the energy spectrum balance is made up of 3 terms: the production, the transfer, and the dissipation. The production part is Pk, which is where the energy is produced, right? And the energy produced means what? If you have a jet flow, the flow is coming in, the fluid is coming in through the nozzle. Energy is being produced at the largest scale. It is being produced at the largest scale. Energy is not being produced at any other scale. It's been produced at a scale corresponding to the width of the flow, the jet diameter. So production is contained in the energy containing range, isn't it? So that is what production is. Energy is produced there. The flow is coming in with a certain amount of energy. That produces the turbulence. That is your production term. The second term is your energy transfer, and because it is an energy transfer rate with respect to wave number, you have it as del K. This is not a typical spectra like you see for production or dissipation or energy spectra for that matter. This is with respect to wave number, because it changes with respect to wave number. It goes from the lower wave numbers to the higher wave numbers, isn't it? So that is your spectral transfer. And your dissipation is a term that we have seen before, 2 nu kappa squared EF kappa. That is your dissipation. Now what we tried to do was that the first term is pretty clear. The production term is pretty clear. The production term has to do with, this has to do with the contribution to the production at the wave numbers kappa A to kappa B, isn't it? It has to do with the contribution to the wave numbers from the production spectrum. The second term though, that is a little bit more complicated because it is the energy that is removed from wave numbers lower than kappa and moved to wave numbers higher than kappa. So that rate of gain of energy is basically that second term integrated from kappa A to kappa B minus del kappa of T of K, Tk of kappa d kappa. So since you are integrating a derivative, you will actually get that term exactly, isn't it? Because the derivative goes away. So what you have is T kappa kappa A minus T kappa kappa B. So that is the important point. If you want to take the energy transfer rate over a certain range, it's basically the difference of the endpoints. So essentially, the transfer has no contribution to the total turbulent kinetic energy. Doesn't that make sense? Because T of 0 is 0 and T of infinity is 0. So T kappa at 0 is 0 and T kappa at infinity is 0 because there is no energy or there are no scales below 0 and there are no scales above infinity. So there's nothing to transfer to. So the endpoints are 0. And that is what we mean by this. Since T kappa vanishes at 0 and infinite wave number, the transfer term makes no contribution to the balance of TKE. It makes no contribution. So the final term is the dissipation term, which we know what we get when we integrate it. All right, we get the dissipation, we get the actual dissipation. And that is what we are trying to show with these plots. So E of kappa is more dominant in the energy containing range, whereas dissipation, the D of kappa is more dominant in the dissipation range. The production is more dominant in the energy containing range. And del kappa of T kappa, it is negative here in the energy containing range. Why? Because the energy is being removed from there. And it is positive in the dissipation range because energy is being added there. The transfer term itself starts from 0. It keeps increasing. It peaks in the inertial subrange and then it keeps decreasing to 0. Now we will analyze each of these ranges and find out what happens when you integrate each of these terms and put this in the energy spectrum balance equation next. I hope this was clear. Thank you.